Imagine spending 3 whole days, just pulling your hair out over a single incorrect bit.
Oh, yeah, that is absolutely brutal.
Right. 3 entire days of debugging only to finally discover that your code is actually perfect.
Which is almost worse, honestly.
It really is. The syntax is flawless, the logic is totally sound, but your AI assistant is just confidently lying to you.
All because of one bad comment.
Exactly. One bad comment left in a configuration file years ago. It sounds like, a modern developer's worst nightmare.
Oh, without a doubt.
So, how do you prevent this? Well, you build a system where you stop trusting the software completely.
You stop trusting the AI.
Yep. And you make the physical silicon the ultimate, unarguable referee.
It is the absolute definition of a truth-seeking mission, really.
It is. And that brings us to the mission of our deep dive today.
Because when you strip away all those layers of interpretation that we usually rely on, you're left with a very stark reality.
Right. The machine either does what you told it to do in the physical world or it doesn't.
There's no place for a hallucination to hide when you're literally looking at raw voltage.
And we've got a really fascinating stack of sources to go through for you today. We're talking architectural diagrams, raw wiki entries, developer logs, technical blog posts.
It's a goldmine of data.
Yeah, it really is. Together, they outline this incredible pursuit of unvarnished truth in software and hardware development.
We are going to explore this custom-built, silicon-verified workflow.
And the best part, this wasn't built by some massive tech conglomerate with unlimited funding.
No, not at all.
It was created by a retired electronics technician. We'll call him Terry.
Terry has 50 years of experience, by the way.
50 years. And he built this entire architecture out of a shed in regional New South Wales, Australia.
It is just a phenomenal case study for anyone listening.
Because in modern firmware development, we really suffer from this profound information overload, don't we?
Oh, incredibly so. We have compilers, operating systems, drivers.
Hardware abstraction layers.
Exactly. All these proxies separating you, the developer, from the actual physical hardware.
And Terry's approach just strips all of that away.
It does. We're going to explore what happens when you force the machine itself to dictate the truth.
And how his specific setup ensures that no code is even allowed to enter his text editor unless it has been physically proven on a microchip first.
Which is such a wild concept.
It blew my mind. I was trying to think of a good way to frame this for you listening right now, and it's basically like trying to get into the world's most exclusive nightclub.
Okay, I like this analogy.
But instead of a bouncer checking your ID or making sure you're on the guest list, the bouncer is checking if you fundamentally obey the laws of physics.
Right. If your code can't prove itself in the theoretical realm, you don't even get to stand in line.
You're just banished instantly.
It's a brilliant way to put it. But to understand how he built this bouncer, we really need to look at why he built it.
Right, which requires getting into the mindset of a veteran technician.
Because we are talking about someone who has been soldering components since the 1970s.
That's a lot of burnt fingers.
Exactly. And when you have spent half a century diagnosing physical components, resistors, capacitors, logic gates.
Your brain is basically wired to suspect the physical world first.
Precisely. Which makes perfect sense when you think about it.
Yeah, if you build a physical circuit and it doesn't work, you look for a short circuit.
You look for a blown capacitor.
Right. So in the sources, we see Terry working with this specific microcontroller, the STM32F051.
Which is a very standard, widely used ARM Cortex M0 chip.
Super common. And he was trying to get this chip to run at its target speed, which is 48 megahertz.
But the chip just completely refused.
Yeah, sometimes it would limp along at lower speeds, and other times it would just throw an unhandled interrupt and crash entirely.
And this is where that 50 years of instinct kicks in.
A traditional hardware developer looking at an intermittent fault like that,
they're immediately going to blame the physical environment. The internal monologue goes straight to the components.
Like, is the crystal oscillator flaky?
Right. Or is the phase-locked loop marginal? Do I have a decoupling problem on my power rail introducing noise?
Because when behavior is intermittent, the physical world is almost always the culprit.
That's the golden rule of hardware.
So the traditional debugging move is to go straight to the physical bench.
You fire up the oscilloscope, you get out the logic analyzer.
And you just start probing the physical pins on the board to see where the electrical signal is degrading.
But the bench gave him a very, very surprising answer.
It did. Terry probed the board, checked the voltages, analyzed the clock signals, and the physical hardware was absolutely flawless.
The power rail was perfectly clean.
The crystal was humming perfectly.
Yeah.
The bench essentially said, hey, don't look at me, I'm doing exactly what I'm told.
Which forces a massive psychological pivot.
Yeah, because if the physical reality is sound, then the ghost has to be in the machine.
It has to be in the abstract logic of the software itself.
And Terry has this core philosophical belief recorded in his wiki that I think every engineer listening to this should print out and frame.
Oh, I know the one you're talking about.
He writes, "He who never made a mistake never made anything."
Such a great quote.
And he actually maintains this massive, comprehensive wiki of all his lessons and errors.
He doesn't treat mistakes as failures to be hidden away.
Not at all. He treats them as the empirical evidence of doing actual engineering work.
I love that perspective.
Yeah.
Mistakes are simply data points. They map the exact boundaries of what is robust.
Exactly.
But more importantly, this particular mistake, chasing a hardware ghost that turned out to be software.
It forced him to reevaluate his own instincts.
It did.
Let me push back on that a bit, though, because, it's easy to romanticize this whole old-school hardware approach.
Sure it is.
But if 50 years of instinct leads you to spend days probing a perfectly good crystal oscillator with an oscilloscope.
When the actual problem is just a bad line of code.
Right. Hasn't that instinct kind of failed? Isn't this exactly the kind of wild goose chase that modern software tooling is supposed to prevent?
Well, that is the exact realization Terry had.
Oh, really?
Yeah. The instinct didn't fail, necessarily, but it had definitely reached the absolute limit of its usefulness in a highly practiced environment.
So it was just outdated for the context.
Exactly. Human instinct is incredibly powerful in the physical domain, but firmware development today has become so staggeringly complex that human guessing is just no longer sufficient.
You can't just guess what thousands of lines of hidden configurations are doing.
You can't. And Terry realized that his traditional intuition was actually a liability here.
So what did he do?
He didn't abandon his skepticism, he automated it.
He automated his own skepticism. I really, really like that framing.
He spent an entire year building a machine that doesn't rely on human guessing at all.
Because human instinct can be led astray by these complex systems, he needed an impartial filter.
Something that wouldn't just assume the crystal was broken because it felt like a hardware bug.
And this leads us directly to the core of his architecture. This is the concept that completely blew my mind when I was reading through the sources.
The Anvil gate.
The Anvil gate. It's a remarkably evocative name, isn't it?
It really is. Striking metal, forging it, and testing its structural integrity under immense physical pressure.
Before it's allowed to be used for anything real.
Exactly.
So let's really dig into this verification process step by step, because it's wild. We need to define what a silicon-verified workflow actually means here.
Because if you're a software developer listening to this, you might just be thinking of a linter.
Right, and a linter is basically a tool that scans your code for syntax typos or stylistic errors before you run it.
But a linter is just software pretending to be clever.
It's just software checking software. The Anvil gate is a physical trial by fire.
The rigidity of it is what makes it so fascinating. Terry uses a programming language called Forth.
Which is an older language, right?
Yeah, from the 1970s. It's deeply highly efficient, and it sits very close to the metal.
Got it. And in Forth, a function is called a word.
Correct. And before any new word is accepted by Terry's development environment, it must pass 7 strictly enforced checks.
Okay, let's walk through those checks because they really build in intensity.
They do.
So step 1 is pretty straightforward. It must have a valid name. You can't just throw garbage characters at the system.
Right. Basic syntax check.
Check number 2 is where it gets very specific to Forth. Its stack comment must parse correctly.
Now, for listeners who might not be familiar with it, Forth is a stack-based language.
Meaning?
Instead of declaring named variables like you would in, say, Python or C,
Right.
you push data onto a memory stack, and operations pop data off that stack.
Ah, okay. So keeping track of what goes on and what comes off is critical.
It's everything. The stack comment is essentially the contract of the function.
It says, I take these 2 integers in and I spit 1 integer out.
Exactly. And if that comment doesn't logically parse, the contract is broken before the code even executes.
It fails instantly. Okay, check number 3, it requires a real explanation.
Yes, you cannot just write a clever piece of code and leave it undocumented,
The system physically demands plain English intent.
which is just a brilliant way to prevent the accumulation of mystery code.
Oh, we've all seen that. Code bases full of functions that work perfectly, but the original developer left the company 3 years ago.
And now nobody dares touch it because they have no idea why it actually works.
Exactly. Okay, so now we cross the boundary from software into the physical world. Check number 4 is hardware integration.
This is where it gets real.
The word you just wrote isn't just simulated on your PC. It is actively executed on an actual physical STM32 microchip sitting on Terry's desk.
Over an SWD debug wire.
Let's explain that. What is SWD?
SWD stands for serial wire debug. It's a 2-pin interface designed by ARM.
So it's a cable.
It's more than just a standard communication cable. It is quite literally a back door into the brain of the microcontroller.
Wow.
It allows you to halt the CPU, inject instructions, and read memory states directly.
So we are entirely out of the simulator at this point.
Completely. The code is sent down that physical wire and executed by the microscopic silicon gates of the chip itself.
Which brings us to check number 5. Once it's down there, the chip's own internal disassembler must show what the word actually compiled to.
You're verifying the translation here, because compilers can be really tricky.
Right, you might write something in Forth, but you need to see exactly how the compiler interpreted that into ARM assembly language.
You are demanding to see the raw machine code that the chip is actually being asked to run.
That is thorough. Okay, check number 6. The connected board's device ID is verified against what the word requires.
This sounds simple, but it's crucial.
It ensures you aren't accidentally trying to run code meant for a completely different piece of hardware, right?
Exactly. If you send a command meant for a motor controller to a delicate temperature sensor, bad things happen.
It eliminates a whole class of incredibly frustrating environmental bugs where the code is right, but the physical context is just wrong.
It's a basic sanity check, but a necessary one.
And finally, we arrive at check number 7.
The ultimate proof.
Yes. The word's mathematical or logical result isn't just checked in the computer's memory. It is actively written into a real GPIO, a general-purpose input-output data register on the physical chip.
And then that exact same value is read back through a completely independent hardware path to verify it.
This is the absolute masterpiece of the Anvil gate. It closes the loop entirely in the physical domain.
For context, a register is essentially a tiny bank of memory on the chip that directly controls physical pins.
So it's not enough to just run the code and say, well, it didn't crash, so I guess it worked.
No, that's not good enough for Terry.
It's like demanding the code write a secret message on a physical piece of paper, lock that paper inside a physical safe, and then having a completely separate security system open the safe to verify the message is actually sitting there.
That's exactly what it is. If the expected value is physically sitting in that silicon register, the word passes.
The philosophy of truth here is just profound.
Hardware registers remain the final arbiter of system state.
Period.
Right. In a world full of emulators, mock objects, and software approximations, independent silicon verification is the absolute, unarguable source of truth.
Because a physical register cannot hallucinate a voltage.
Exactly. It is either a 1 or it is a 0.
And the consequence of failing any of these 7 steps is absolute. If a new piece of code fails, it never even enters the language server.
Terry's text editor won't even suggest it via autocomplete.
It's like it never existed. To the tooling, to the environment, unverified code simply does not exist.
It forces an incredibly rigorous discipline on the developer. You literally cannot build up technical debt if the system physically refuses to recognize unproven code.
Okay, so the Anvil gate is this impenetrable, perfectly logical fortress of truth.
It is.
But reading the sources, that brings up a massive contradiction that I want to get your take on.
Okay, let's hear it.
If the Anvil gate catches every mistake, how did Terry end up with a bug that survived for 3 entire days and stopped his chip from hitting 48 megahertz?
Yes. This is where the story shifts from the mechanics of testing into the psychology of software architecture.
Because even the most rigorous, physically verified gate in the world cannot catch a code base that is fundamentally lying to itself.
Precisely. We have to talk about the tale of the divergent bit fields.
The infamous 3-day bug.
And it all comes down to an inconsistent library. Terry had built up a library of these fourth words over several years.
And hidden deep inside this library, there were two competing conventions for processing bit fields.
Let's clarify bit fields for a second just so everyone's on the same page.
Please do.
In embedded systems, memory is extremely constrained. You don't want to waste a whole 32-bit register just to store a simple true or false value.
Right, that's incredibly inefficient.
So you pack multiple pieces of data into a single register. You might have 1 bit controlling the power, 3 bits controlling the speed, and 4 bits controlling a sensor, all packed into one single address.
And to manipulate them, you need a sequence of operations called bit masking and shifting.
Exactly. And in fourth, because it's a stack-based language, like we mentioned, the exact order in which you provide the arguments, the address, the mask, the value is everything.
It's make or break. So here is the root of the problem. The raw primitive fourth words that act directly on the chip's memory words, like BIS, which stands for bit set, take the address of the memory on top of the stack and the mask underneath it.
That is one very specific structural order.
Right. However, Terry was also using names derived from the manufacturer's CMSS SVD files.
These are essentially the official manufacturer-provided dictionaries for the chip.
And those SVD names push what the sources call a two-value package. They push an address, but they also push a bit position.
So you immediately have two different shapes of data colliding in the system.
Exactly. You have the primitive operation expecting one order on the stack, and the descriptive manufacturer dictionary providing a different package entirely.
And to bridge that gap, helper words were created to unwrap the manufacturer's package and feed it to the primitives.
But here is the divergence. 28 of these helper words in his library unwrapped the package one way, putting the value first.
Right.
But 2 helper words unwrapped it the other way, putting the bit position first.
It's a classic architectural schism.
Yes, the vast majority of the code base agrees on one standard, but a tiny minority operates on a completely contradictory standard.
And I think anyone who has ever written code can guess which 2 helper words were the exact ones Terry was using to configure his 48 megahertz clock.
The contradictory ones.
Of course they were.
But the crazy part is that this was a silent failure. This schism had existed in his library for months, maybe years, and literally nobody noticed.
Why didn't they notice?
Because when the chip was running on its slow, default internal 8 megahertz oscillator, the wrong stack order was somehow close enough.
Close enough in hardware is terrifying.
I know. The bits landed in a way that didn't immediately crash the chip. It just limped along, blissfully unaware of its own internal contradiction.
The concept of tolerance in complex systems is fascinating here. At low speeds, the system had enough slack to absorb the incorrect instruction without triggering a catastrophic fault.
The error was always there mathematically, but the physical environment wasn't stressful enough to expose it.
Exactly. The fault only reared its head when he tried to bring up the 48 megahertz clock.
Right. To get 48 megahertz, you have to take the 8 megahertz crystal and you multiply it using a phase-locked loop, or a PLL, with a multiplier of 6.
And that higher speed demanded absolute precision.
And suddenly, those incorrectly unracked bit fields resulted in intermittent, unhandled interrupts. The system essentially tore itself apart under the stress.
It raises a really vital question about how we tolerate latent defects in engineering.
Yeah, why do we let things limp along in software when we would never accept it in physical construction?
We just wouldn't.
I was thinking about this, and it's like having a car with a slightly wobbly wheel.
Okay, I can picture that.
When you're just driving around your neighborhood at 20 miles an hour, the steering wheel shakes a tiny bit, but you ignore it. It's fine. The car still gets you to the grocery store.
Right.
But then you take it on the highway, you hit 70 miles an hour, and suddenly the steering wheel is vibrating violently out of your hands, and the whole suspension is threatening to fall apart.
The flaw was always there in the wheel. The speed just amplified it until it couldn't be ignored anymore.
That analogy perfectly captures the paradox of the Anvil gate in this scenario.
Because the original contradictory bit field words, the ones with the wrong stack order, they actually did pass the Anvil gate individually.
Wait, let me stop you there. Does that mean the gate failed? I thought the whole point of the Anvil gate was that it caught everything.
Well, they passed because technically, mechanically, they executed and produced a result.
So the gate asked the specific word, can you toggle a bit at this location?
And the word said, yes, I can. The failure wasn't mechanical at the micro level. It was a systemic contradiction at the macro level.
Ah, I see.
The word worked in isolation, but it completely disagreed with the architecture of the universe it lived in.
So how did he untangle it?
He had to step back and look at the entire family of words. Terry had to redefine the whole set so that every single word takes the exact same shape on the stack. Value, address, bit position.
He standardized the stack order universally across the library.
He forced a complete conformity.
And then he took those newly reconciled uniform words and he ran them all back through the Anvil gate.
And suddenly, harmony was restored.
The gate ensured the word worked mechanically, but the human architectural consistency ensured the system could actually survive under the immense pressure of running at 48 megahertz.
It beautifully illustrates why iterative layers of testing are absolutely required.
You can't just rely on one check.
Right. Verification at the micro level, the gate, is essential. But it cannot replace macro-level architectural coherence. You need both to build a truly resilient system.
Okay, so the stack order is fixed, the library is unified, Terry can finally run the code to switch the clock to 48 megahertz.
Finally.
He executes it, and the system still hangs.
Oh no.
It just sits there doing nothing. Why? Because sometimes, even when the code is absolutely right, the test that is observing the hardware is completely blind.
This is a masterclass in the philosophy of automated testing.
It really is.
As developers, we almost universally assume that if a test fails, the system under test is broken.
We rarely stop to assume that the test itself might be the liar.
Exactly. Let's walk through the mechanics of this clock switch, because it's a very specific choreography on this silicon.
Yeah, to switch a microcontroller to 48 megahertz, Terry has to first enable the external crystal oscillator.
Then he has to wait for a hardware flag confirming the crystal is stable.
Next, he sets the PLL multiplier to 6. He enables the PLL. He waits for the PLL to lock onto the frequency.
Then he switches the system clock source over to the PLL.
And finally, the last crucial step. He has to wait for the switch to confirm it actually happened.
It's an intricate dance. And that final step is the critical point of failure here. It's called the System Clock Switch Status Check, or SWS.
The SWS check. It involves polling a specific field in a hardware register until it reads a specific value.
In this case, it needs to read 10 in binary.
Which translates to the number 2 in decimal. When that specific field reads 10, it means the hardware has successfully confirmed that the PLL has taken over as the main clock.
So the software basically enters a loop, constantly asking the hardware, are you at 10 yet? Are you at 10 yet?
Exactly. But Terry had used a fourth word called BIF-AT to do this polling. And here was the fatal flaw.
What was it?
BIF-AT was designed as a single-bit tester. It was only written to look at the lowest bit of whatever field it was given.
Oh, I see the collision course here.
Right. When the physical chip successfully switched to the PLL, the hardware field changed to 10, just like it was supposed to.
But the software loop was using a word that only looked at the low bit.
And the low bit of 10 is...
0.
Yes. So the loop kept asking the lowest bit, are you set? Are you a 1?
And hardware was truthfully, accurately answering, no, I'm a 0.
Because the 1 was sitting right next to it in the higher bit position.
The revelation here is stunning. The chip was actually running perfectly at 48 megahertz.
The hardware had completely succeeded in its task. The physical silicon was victorious.
But the software test was stuck in an infinite loop, waiting for a condition that would never arrive.
Because it was looking through a tiny keyhole instead of just opening the door to look at the whole room.
It is an incredible illustration of observer bias in programming. The act of measuring it incorrectly convinced the developer that the system was broken.
Think about it like this. Imagine you ask a friend to check if a traffic light has turned green so you can hit the gas.
Okay.
But your friend is severely colorblind, and they're only looking at the physical position of the bottom bulb on the traffic pole.
Right.
The light has actually changed to a green arrow, which happens to be in a different physical spot on the pole. Traffic is moving, cars are honking, everything is working perfectly, but your observer is sitting in the passenger seat screaming, "Stop! The bottom bulb is dark."
That is precisely the dynamic. The
Yeah.
test was fundamentally blind to the physical reality of the system state.
So the fix was elegantly simple once he saw it. He had to generalize that BIF-AT word so that it could read multi-bit fields.
He updated it to require the width of the field, not just the starting position.
He ran that new generalized word through the Anvil gate to physically prove it worked.
Yeah.
And then he compared the whole 2-bit field to 10.
Boom! The loop exited instantly. The test passed.
This points out a crucial lesson in automation that is so often missed. Never assume the silicon is failing when the observer, the test code, might be fundamentally flawed.
You always have to verify the verifier.
Always.
This is exactly where manual, low-level inspection of the raw data becomes critical. If you rely blindly on an abstracted test, you will chase ghosts forever.
Speaking of chasing ghosts, that brings us to the next massive hurdle. The test was fixed, the observer was no longer blind, the clock was finally running.
Success.
Terry checks the output frequency, and the clock is only running at 24 megahertz, exactly half the intended speed.
Half speed. In digital logic, a discrepancy of exactly half implies a very specific mathematical routing error early in the chain.
Let's look at the math of the phase-locked loop. A PLL essentially multiplies its input frequency.
If the input is the 8 megahertz external crystal, and you multiply it by 6, you get your 48 megahertz target.
However, the STM32 also has an internal oscillator that runs at 8 megahertz.
And often, for stability reasons, that internal oscillator is divided by 2 before it ever hits the PLL.
So internal 8 megahertz divided by 2 is 4 megahertz. Multiply that by 6 and you get exactly 24 megahertz.
So the math tells us exactly what the hardware was doing. The chip was pulling from the internal oscillator, not the external crystal.
The source selection was wrong.
The source selection field in the configuration code was incorrectly set to the value 1, which routed the internal oscillator divided by 2.
It was supposed to be set to 10, which would have routed the external crystal.
A simple typo, one single bit wrong, change the 1 to a 10, and you hit your target.
Yes, but why was it set to 1 in the first place? And why did it take so long to find?
This leads us to what is arguably the most dangerous element of modern coding, and the absolute centerpiece of Terry's shed-based revolution.
Trusting the confidence of artificial intelligence.
The introduction of the AI layer. This is where the story gets incredibly modern.
Meet CODA. CODA is a local large language model, an AI running right there on 2 GPUs in Terry's setup.
CODA is designed to be his interactive assistant.
And running a local model is smart. It gives you privacy, low latency, and offline capability.
But it doesn't matter if it's local or in the cloud. It is still subject to the fundamental architectural flaws of all LLMs.
True. So in Terry's configuration file, there was a hard-coded value of 1. But right next to that value, there was a human-written comment.
And the comment explicitly claimed, in plain English, that this value selected the external crystal.
A classic case of code rot. At some point in the past, the code changed, but the human forgot to update the comment.
The semantic meaning drifted completely away from the physical reality.
Terry is confused as to why the chip is running at half speed. So he goes into his chat interface and he asks CODA, his AI assistant, hey, what value selects the external crystal?
CODA scans the file, reads the human-written comment, and confidently replies. The value 1 selects the external crystal.
The AI betrayed him. It prioritized the adjacent human text over the actual data logic of the system.
It confidently repeated the lie.
Yeah.
Both the comment and the AI were completely wrong.
But because CODA was so authoritative and conversational, Terry didn't question it immediately.
This highlights the immense peril of using LLMs in highly technical deterministic domains.
Right, because LLMs are designed to be helpful.
Their fundamental architecture is to predict the most likely next token based on the context window. If the context window, the comment strongly asserts that X is true, the model will confidently assert X, even if the manufacturer's datasheet sitting on the hard drive contradicts it.
They lack an intrinsic grounding in factual reality unless they're explicitly forced into it.
They're semantic engines, not truth engines.
So how did Terry fix this? He realized he couldn't trust the text in the code base, and he couldn't trust the text generated by the AI.
He needed the objective truth. He needed the datasheet.
But modern reference manuals for these microcontrollers are thousands of pages long.
And the section on clock configurations is famously a nightmare. It's a massive flowchart called the clock tree.
The clock tree diagram, yes, those are notoriously complex to parse.
It's a labyrinth of multiplexers, prescalers, dividers, and logic gates, showing exactly how the heartbeat of the chip is routed to dozens of different peripherals.
Humans stare at them for hours, tracing a single line with their finger.
Terry does something brilliant here, though.
He takes a screenshot of this incredibly complex clock tree diagram directly from the manufacturer's PDF.
He doesn't copy the text. He takes a picture of the flowchart.
And he feeds this image back into CODA, the exact same AI that just lied to him moments ago.
Engaging the multimodal capabilities of the model.
Exactly. He uses CODA as what the sources call an image-to-common-sense converter.
And something amazing happens.
By forcing CODA to look at the visual representation of the logic gates, rather than the text-based comments in the code, CODA accurately parses the diagram.
The vision model processes the edges and the flow of the diagram entirely differently than the language model processes semantics.
It traces the lines, bypasses the text hallucination entirely, and replies correctly. According to the diagram, the value 10 is required to select the external crystal.
That is a stunning reversal. The visual structure forced the model to perform spatial and logical deduction rather than just textual synthesis.
Let's really appreciate the irony here. The exact same AI model that confidently lied to his face was the one that ultimately gave him the right answer.
That's like having a terrible navigator in your car who gets you completely lost because they are reading the map upside down.
But then you tell them to look out the window, and they correctly identify a massive mountain and get you back on track.
It perfectly highlights the dual nature of these models. They are incredible synthesizers of structural and visual data.
When given a complex diagram, they can extract the topology faster than a human.
But they are terrible guardians of absolute fact when left to just text, because they aim to align with the text around them.
If the human comment lies, the AI lies.
Which necessitates a systemic boundary. Terry realized he couldn't just have Coda freely hallucinating facts about hardware states.
He needed a way to harness its visual and analytical power without ever letting it guess about physical reality.
And that realization birthed the ultimate architecture of his workflow.
This is where he stops being just a hardware technician and becomes a true systems architect. Let's talk about the scribe and the referee.
This is the culmination of the entire experiment. He designed a system that fundamentally mistrusts the AI while still utilizing it to its maximum potential.
We talked about how the Buffett test was blind. We talked about how Coda hallucinated. Terry's solution to all of this is an absolute masterclass in modern automated testing design.
He created a dual host setup.
Meaning two distinct entities operating simultaneously in the development environment.
Right. There's Coda, the AI, and then there's a new tool he wrote called Regmon.
Regmon stands for Register Monitor. But Regmon isn't just a background script running invisibly. Terry brought Regmon into the chat room as a literal crew member alongside Coda.
So you have a human developer, an AI language model, and a deterministic software tool all interacting in a shared conversational space.
Exactly. And Terry strictly defined their roles. Coda is designated as the scribe.
Coda's job is to write the narrative, keep the paper trail, reason about the overarching design, parse the visual diagrams, and generate the raw fourth code.
And Regmon's role.
Regmon is the referee. Regmon is a deterministic software agent. It has absolutely no language model in its factual path.
It is fundamentally incapable of hallucination.
Because it doesn't generate text, it queries reality. How does that interaction actually work to eliminate the AI hallucinations?
Terry established a strict, unbreakable rule in the chat room. Coda is never, ever allowed to state a fact about the chip's current state.
If Coda is generating code and needs to know what the clock speed is or what value is currently sitting in a specific register, Coda cannot guess.
It must literally type out a query to the @Regmon agent in the chat.
It forces the AI to consult the instrument, just like a scientist consulting a thermometer.
Exactly. Coda asks in the chat, @Regmon, what is the value of the PLL source register?
Regmon receives that command, reaches down through that SWD physical wire we talked about earlier, reads the live voltage registers on the actual silicon,
Computes the answer using a Python script, and posts the deterministic, unarguable truth back into the chat for Coda to use.
But where does Regmon get its definitions? If you tell it to look at the PLL source register, how does it know what physical hex address that corresponds to on the silicon?
That is the most brilliant part, and it leads to the death of the manual datasheet.
Oh, really?
Yes. Regmon gets its definitions from an SVD database. SVD stands for System View Description.
It is a massive XML file standard provided by ARM and the chip manufacturers.
It maps out every single register, every bit field, every memory address on the chip in a machine-readable format.
So instead of a human reading a 2,000-page PDF and manually typing the hex addresses into the code, which is where typos happen, the machine reads the machine-readable datasheet directly.
Yes. Terry took those raw manufacturer SVD files and ingested them into a relational database.
Regmon queries that database, gets the exact physical address, reads the silicon over the debug wire, and tells the AI the answer.
Terry hasn't opened a technical manual PDF in weeks.
The datasheet is now consulted entirely by the machine, not by the man.
This is a profound paradigm shift. For decades, embedded development meant a human acting as the slow, error-prone translation layer between a massive English document and a compiler.
Carrie has automated the translation layer. The system reads the spec, the system queries the silicon, and the system corrects the AI.
So, based on Terry's shed-based masterclass, what is the checklist for you, the listener, if you want to build your own silicon-verified workflow? Let's break it down into 5 actionable steps for setting up an automated hardware verification environment today.
This is highly applicable for anyone doing firmware or hardware-adjacent software.
Number 1, establish a live, unabstracted connection to your hardware.
You need a physical debug wire, like SWD or JTAG. You need to be able to touch the silicon directly, not just talk to an operating system.
Number 2, implement a deterministic register monitor, your own version of Regmon.
You need a tool that can read the physical state of the hardware in real time, without any caching or software abstraction getting in the way.
Number 3, build your own Anvil gate.
You need a rigorous compilation and testing process, flash the code, execute it on the physical chip, and critically, read back the physical result.
And this gate must actively block unverified code from your development environment. If it isn't proven on the chip, your editor shouldn't even know it exists.
Number 4, ingest raw manufacturer data. Stop reading PDFs.
Use SVD files or other machine-readable specs to build a database. Let your tools derive their constants directly from the source material.
And finally, number 5, confine your AI.
If you use AI assistants, treat them strictly as scribes. Confine them to reasoning, structuring, and parsing visual data.
Strictly separate them from factual hardware reporting. Force them to query your deterministic monitors for the truth. Never let the language model guess a hardware state.
That 5-step checklist is incredibly robust. It mitigates human error, eliminates AI hallucination, and grounds the entire development process in physical reality.
Let me play devil's advocate here, though. I can hear people listening to this right now thinking, this sounds like an unbelievable amount of work.
Do we all really need to build an elaborate AI chat room with a scribe and a referee just to blink an LED on a hobby board?
For blinking an LED, no. But for developing a complex real-time operating system, a medical device controller, or an automotive braking system, absolutely yes.
While the specific chat room interface Terry built is novel and tailored to his shed, the underlying principle is universal and critical.
The principle of iterative verification layers.
Building these layers where a monitor feeds a hardware gate, which feeds a language server, which feeds an AI, creates a compounding effect.
Yes, it takes a year to build the setup, but once it's built, it drastically accelerates development speed.
You are no longer spending 3 days hunting for a single incorrect bit because a comment lied to you.
You find that error in 3 seconds because the silicon gate rejects it instantly.
It turns weeks of debugging nightmares into quiet, highly productive afternoons.
It turns debugging nightmares into quiet afternoons. I absolutely love that.
Let's summarize this incredible journey we've been on. We started with a veteran technician whose 50 years of soldering instincts told him to check the physical crystal.
But the reality of modern firmware forced him to evolve those instincts into automated skepticism.
We saw how a stubborn stack order bug in a Bitfield library remained invisible because the system wasn't under enough stress, proving that architectural inconsistency is silent until it faults.
We examine the philosophical danger of tests that are blind to reality, the colorblind traffic light observer, and how generalized multi-bit reads are necessary to see the whole picture.
We witnessed the betrayal of an AI that confidently hallucinated facts based on a bad comment, and how visual data, the clock tree diagram, was the key to forcing the AI into logical deduction rather than textual guessing.
And finally, we explored the ultimate architecture. The registers of the referee, the AI as the scribe, and the machine-readable datasheet eliminates the human translation error.
It's a system where the physical silicon is the only source of truth, and the rest of the software stack is just trying to write down what the registers say accurately.
It is a profound demonstration of how we must adapt our engineering practices as our tools become more abstract and more artificially intelligent.
Which leaves me with a final provocative thought for you to mull over as we wrap up this deep dive. If you've written code recently, you know we are rapidly moving toward a future where AI language models might write the vast majority of our boilerplate code.
If that happens, then human developers are no longer really coders in the traditional sense.
What do we become then?
We become epistemologists.
Exactly. Our entire job, our only real value, will be studying the nature of truth.
We will be the architects designing the physical traps, the Anvil gates, and the deterministic monitors that force the machine to physically prove it isn't lying to us.
So ask yourself, in your own projects, in your own workflow, how secure are your gates? Are you relying on the shadow play or are you looking directly at the light? Something to think about.